Okay, so this is section 4.3. This is called the Fundamental Theorem of Calculus. Just by the title alone, you should probably understand that this is a pretty important section in calculus. This is actually kind of where it all started, to be honest with you. There are two parts to the fundamental theorem. It's part 1 and part 2. We're actually going to talk about part 2 first. It actually is going to make things a little bit easier to understand when it comes to part 1. So part 2, which is also the one that we use most, says that if f is a continuous function on a closed interval from a to b, then the integral from a to b of f of x dx equals capital F of b minus capital F of a. And don't forget, the capital is the antiderivative of lowercase f. So really what that's saying is take the antiderivative of f of x, plug in b, plug in a, subtract them, and we're going to get the integral. This is basically the shortcut, just like we did with derivatives, how we did the really long limit definition of derivatives. We've done the limit definition for the limit of sums, which is the integral. This is the shortcut to it. Now, there is a stipulation, which is where the part 1 of this comes in. Not everything that we're going to have, we're going to be able to take an antiderivative of. So we will see that when we go through it. All right, so the results of the fundamental theorem of calculus, if you can find the antiderivative of lowercase f, and that's the big if you can do that, you can evaluate the definite integral without that limit of sums, without doing the whole delta x and x sub I and f of x sub I. You can do it without doing all that. And I'm actually going to cross this out. I do not like this notation right there. We're going to use the one that you actually saw in the box above. It just says that the antiderivative, we'll find the antiderivative, then we're going to evaluate, that little bar means to evaluate, the antiderivative at b and at a and subtract them. So that is the same as f of b minus f of a. This is the shortcut. This is the fundamental theorem, technically part 2. And that's a way to find the integral of a function. So why is it not necessary to include c here? Well, the basic idea is that if we could include the c, but the c values are going to subtract to 0. So the c values will always subtract to 0. And that's in the case of a definite integral. So you could have on this one up here f of b plus c minus f of a plus c, but the c's are going to subtract out every single time. So we don't need the plus c. Okay, so let's do a quick example. The first example says, I want to find the integral from -2 to 3 of 6x squared minus 5. Normally you would have had to have found your x sub I and your delta x. Your delta x would have been, 3 minus -2 over n, so it would have been 5 over n. Your x sub I, you'd have to do -2 plus delta x times I and plug all that stuff into your function. It would get a little bit tedious. You could do it, but it wouldn't be a short problem. This will make it much shorter. It just says, if I want to take the integral and I can find the antiderivative, which I can, we're going to do that. So let's find the antiderivative of 6x squared minus 5. The antiderivative of 6x squared, raising the exponent by 1, is 3. Dividing the 6 by the 3 now gives me a 2. And then the antiderivative of 5 is 5x. There is your capital F of x. That's the antiderivative. We're going to take that and we're going to evaluate it at the endpoints and then subtract. So again, mental math, doing some algebra, going to be important here. We're going to plug 3 in. 3 cubed is 27 times 2 is 54. Minus 5 times 3 is 15. So that's what I get when I plug in 3. Then we're going to subtract what we get when we plug in -2. -2 cubed is -8 times 2 is negative 16. And then negative 5 times negative 2 is plus 10. So then we just go ahead and add these two things together, and we're going to see what we get. So 54 minus 15 is 39 minus negative 6. So we're going to get 45. Probably a much shorter process than doing the limit of sums. Okay? So the second problem says find the area under y equals sine of x above the x-axis between 0 and pi. So ultimately, if we just kind of sketch what that looks like, we are talking about graph of y equals sine of x from 0 to pi. Well, sine starts at 0, comes back down at pi. So there we go. We are trying to find this area right here. All right, so according to that, we got to take an integral. So we're going to do the integral from 0 to pi. The function is sine of x. Dx gives you the base of all the rectangles. So what is the antiderivative of sine of x? It is negative cosine of x. We will evaluate that, put our evaluation bar from 0 to pi. So we're going to plug in pi first, so we get negative cosine of pi minus negative cosine of 0. So cosine of pi is negative 1. The negative out in front makes it positive 1. Minus. Cosine of 0 is 1, so we're going to get minus a negative 1 from the inside of there. So 1 minus negative 1 is 2. So that area in the graph between sine of x and the x-axis from 0 to pi is 2. Okay? Hopefully you can see how this is definitely making things easier. Sometimes doing the integral might be easier to do using graphs. Sometimes it might not be. In the case of an absolute value function, this is a little bit different. So in an absolute value function, what you need to do is you need to find the values of the inside the absolute value that make the inside of the absolute value 0, because that's where the function is going to change sign. Remember that your general absolute value function kind of looks like the v. Well, as you know, one of the slopes is negative, the other one is positive. What we need to figure out here is where that's the case, where you've got the negative and the positive slope. So what you should see is the inside of this, x minus 1 equals 0. So x equals 1 is going to be where this thing changes. It's going to change from a negative slope to a positive slope, or vice versa. That's where we have to split our integral. You have to do two separate integrals here because of the fact that this thing will come to a point. So we're going to have to split our integral from 0 to 1 of x minus 1 dx plus the integral from 1 to 3 of x minus 1 dx. Now you might say to yourself, wait a minute, that just looks like using one of our properties, that would be 0 to 3 of x minus 1 dx. You're right, it would be. I have to still do one more thing. We have to check to see where the function would have been negative and where the function would have been positive. So if I were to take some number from 0 to 1 or from 1 to 3, something in between either one of those intervals, and check it. For example, on this one right here, if I were to check a number in between 1 and 3, you cannot use the endpoints. You've got to use a number in between. So if I take 2 and plug it into x minus 1, I would get 2 minus 1, which is a positive value. So this one doesn't need to change. It's already positive. The other one probably is going to have to change. So if I were to plug in something like a half into there, a half minus 1 is negative, which means that this is going to give us the wrong sign. So in order to change that, we need to throw a negative out in front. And that will make everything positive, because remember that this is an absolute value, so all of the areas here should be positive. If we hadn't done it that way, we would have ended up with negative values, and this would have been all wrong. All right, so now we can go ahead and continue by taking antiderivatives. So don't forget your negative out in front, but take the antiderivative. So the antiderivative of x is 1/2 x squared. Antiderivative of 1 is x. And we will evaluate that from 0 to 1. Plus, good thing about this is you've already done the antiderivative. It's going to be the same antiderivative, 1/2 x squared minus 1, but it's going to be evaluated from 1 to 3. So now we've got basically two separate ones to work with. The first one, we'll plug in 1. So again, I'm going to keep that negative out in the front. Plugging in 1, I'm going to get 1/2 minus 1 minus, plugging in 0, I get 0 minus 0, so that's just 0. Plus, now we'll do the second one. I'm going to get, let's see, plugging in a 3, I'm going to get 9/2 minus 1 minus, plugging in the 1, we're going to get 1/2 minus 1. And then we're going to go ahead and simplify all this stuff. So in the first parentheses, we get 1/2 minus 1, which is negative 1/2. But the negative out in the front makes it a positive 1/2. So we get 1/2 from that whole thing. In the second parentheses, I'm going to do this a little bit differently mentally here. I'm going to have a 9/2 minus a 1/2. That's 8/2, but that's 4. And then I have a negative 1 minus a negative 1, which is negative 1 plus 1. So that goes away. So really all I have left out of that one is plus 4. So I get 1/2 plus 4, which is the same thing as 9/2. I know I kind of ran into my next one here, but that's okay. So I said that you could do this one in two different ways. We could also have done this one by areas, which probably would have been easier. Because if you think about it, this is the absolute value of x, which has been shifted 1 unit to the right. So now it looks like this. And we are only interested in the integral from 0, which is right here, to 3, which is about out here. 0 to 3. And we already know that that's 1. So really, I could have done this by doing areas. If I just create a triangle here, because I'm doing the area here and the area here, well, it's just two triangles. The area of this triangle, 1/2 base times height, because that is also going to be a 1 right there. So the height and the base are 1. Half of that is 1/2. And this one, see, the base here is 2, and the height here is also 2. So we're going to get 2 times 2, which is 4. Half of that, no, that's not right. All right, so something's not right here, because, oh, I see what my mistake was. And none of you said anything. Shame on you. My antiderivative in the second one up here was incorrect. Instead of the x, I put a 1. So let's fix that. That's x. That's going to change things. So that's going to be 9/2 minus 3. Okay, I can't just write over top of this one. I'm going to have to actually erase it. 9/2 minus 3, and then minus 1/2 minus 1. That's still 1 there. Okay. That's going to make a big difference. That's going to change this, because I was going to say otherwise this isn't working out. So we're going to get, that's still going to be 9/2 minus 1/2. That's 4. Then we've got negative 3 minus negative 1. So negative 3 plus 1 is negative 2. So 4 minus 2 is 2. That makes much more sense. It's going to give us an area of 5/2, because that's what we're going to get over here in the graph. Because this area right here is base times height, which is 2 times 2, which is 4, but half of that is 2. So we still get 1/2 plus 2. All right, well, if nothing else, that was a good check. I just messed up on my antiderivative. All right, well, anyway, you can see that probably doing the areas would have been easier in this case, doing areas of two triangles. But you do need to know how to take the antiderivative or an integral of an absolute value. The biggest thing is to figure out where the absolute value changes or where it splits. So set the inside equal to 0, and then check points in between the bounds that you've created to see where you might get negative values. If you get a negative value, you have to negate that by putting the negative out in front of the integral. All right, let's move on. The rest of these won't be quite as challenging. So the integral from 1 to 4 of 1 over the square root of x dx. So the first thing we want to do is we want to change that to be the integral from 1 to 4. We're going to bring the square root up to the top and make it a negative exponent. So a square root is a half, so we'll make that x to the negative 1/2 power dx. And now we can go ahead and use our antiderivative techniques, which says raise the exponent by 1, so x to the 1/2, divide by the new exponent. Dividing by a half is the same thing as multiplying by the reciprocal, 2. So we're going to get that for our antiderivative. We will evaluate that at both of our bounds. So we will get 2 times the square root of 4 minus 2 times the, oops, didn't need the parentheses, square root of 1. 2 times the square root of 4. Square root of 4 is 2, so 2 times 2 is 4, minus 2 times 1, so we get 2. Again, this makes things much quicker, much easier to deal with. All right, let's do one more of these before we move on to part 1. Again, general idea, take the antiderivative, which we can do. The antiderivative of 2x is going to be x squared. Antiderivative of minus 1 is minus x. I didn't mess up this time. We will evaluate that from negative 1 to 2. Always plug in the upper bound first. So that's going to be 4 minus 2. And then subtract what you get when you plug in the lower bound. Negative 1 squared is positive 1 minus a negative 1. So here we're going to get 2 minus 1 plus 1 is going to be 2. So we're going to get 2 minus 2, which is 0. Interesting. So that's saying that the integral of 2x minus 1 from negative 1 to 2 is 0. What does that mean? Well, what it really means is that the area above the curve, above the x-axis, and below the x-axis happen to be exactly the same thing. They're basically canceling each other out. It doesn't mean that you actually have a 0 area. You have an area, but they cancel each other out on the top and the bottom. So graphically, this thing is a line. You would be able to graph that and see that that's the case. Okay, we're going to move on to the fundamental theorem of calculus, part 1. I know it's kind of backwards to do it this way, but again, I think that doing part 2 will help to see that part 1 works. So it says if f is continuous on the closed interval from a to b, then g defined by, and this is important, the function g of x is defined as an integral. That is very important. You can have an integral as a function. And the important thing is that you see that it's a function of x. One of the bounds is x, which means that at least one of my bounds can vary. It's going to vary dependent upon x. And then you've got some function of a different variable t. Okay? So that's very important to see. So again, you can define a function, g of x, as an integral. It can be done that way. If that's the case, and it's continuous on a to b and differentiable, and g prime of x equals f of x, or in other words, if I were to take the derivative of both sides of this equation, this is important. If I were to take the derivative of this, that's g prime of x. If I were to take the derivative of this, that's this piece right here. It literally just says I'm plugging the derivative in front of the integral. Well, the derivative with respect to x of the integral from a to x, where a is a constant, of f of t dt is just f of x. Okay, we're actually going to elaborate on that. It says FTC1 just states. I've kind of said that in words, but I'm not going to write it down because there's more to this that I want to get to. But if this is all it is, and this is just an x, not something else, not x squared, not 5x cubed, just x, you're just going to plug the x in for your t values. That's it. So let's go ahead and actually what we're going to do is we're going to pause this video right here. We'll come back. We will do a second video which should finish this up.